tell us about some research that's being done in the Department of Chemistry on the performance of students there. I want to remind you that this series will continue through the term every other Wednesday, and our next speaker will be from Purdue University. He's going to talk about the Signals Project. John Campbell, who's one of the associate vice somethings for IT at Purdue. I should remember, but I don't. Anyway, that should be an interesting talk too. So our speakers today are Rebecca Matz and Mark Banaszak Holl, and they will talk about what's been going on in chemistry.
Thanks. About a decade ago, in my department, looking out over how better to teach the chemistry year to get a better experience in terms of learning the field and getting interested in the field. And to put that together, I'd been imagining this thing that I was calling studio chemistry. The idea was to make sure that the chemistry students were getting to function more like you would an art student in a studio. In other words, give them some brushes and some paints and let them draw some pictures rather than lecture to them about pictures when you want them to learn how to do art. And so that was the fundamental concept. We created the studio course. We had with the lecture system. We changed the way the course was graded. We changed lots of evaluation approaches. And after we'd run the course for a long time, we wanted to know, well, was anything mattering? And were we doing well? Now, we had some anecdotal evidence that was really interesting. One of the pieces of anecdotal evidence was that we had gone from having roughly a 10%, 15% failure rate out of our Gen Chem class to a 0% failure rate out of the studio course. And we basically come up with something where most students could make it through with a C or better. So we weren't losing all kinds of people that were getting lost in our regular class. We were wondering why that was. So we had retention was an interesting thing. And it also appeared that some students were doing better, and we wanted to understand that well. So as I was sitting there trying to figure out how we were going to understand this, my initial cohort of wonderful colleagues had left. Amy Gottfried had transitioned to being a full-time lecturer in our department. We've helped develop the studio course. Ryan Sweeter had become a professor at MSU up the road, and I needed somebody new to work with. And so when Becky was a new graduate student in the group, I said, we really need to understand how this course works. Are you interested? And kind of laid out what we were going to do. And of course, like any good research project, what she's going to show you is not what I described to her in my office that day. It's related, but it's not at all what I said it was going to be, of course, right? And so because that it's not going to be what I said and that she's put so much effort in, I'm actually going to sit down and I'm happy to help field questions at the end and talk about what's happened. But Becky's going to actually now go ahead and show you what is a chapter from her dissertation, which she'll be defending soon. And it's really been part of her overall graduate research here at the University of Michigan.
All right. Thank you. Thanks for coming this afternoon, everybody. So today I'm going to tell you about the effect of concurrent enrollment in our general chemistry course here at Michigan. So my email's here, and I'm sure we can get Mark's too if you have questions afterwards. So it's no secret that laboratories are important tools for teaching and learning in the sciences. They've been employed to help students for over 100 years in engaging with scientific phenomena. You can see these other positives of labs here. They help students gain favorable attitudes towards science. They help students gain some problem-solving abilities. They improve their practical skills. And because laboratories have been found to promote learning in so many different disciplinary contexts, they've really become a cornerstone of science education across the natural sciences. So the National Research Council in 2006 published a study that outlined 7 specific learning goals for science laboratories. You can see them here. I highlighted 2 because the goals for science lectures are often similar, or are similar to these 7 goals here, but the 2 that I've highlighted are really especially and uniquely suited for helping students achieve the highlighted goals. So developing practical skills is not something you can usually do without a laboratory type education, and also the ambiguity of empirical work and understanding when to make decisions in the laboratory is really something that is pretty laboratory specific. Now, as a graduate student, as someone who's never really had to deal with funding, I don't really know all the ins and outs of this, but it's also no secret that laboratories are expensive to staff and run. So budget restrictions, safety concerns, and especially at the high school level, increased attention to standardized exam scores has really contributed to a reduction in time that students are able to spend doing laboratory work, and in some cases, they've been instrumental in elimination of wet laboratory experiences altogether. There's been a few examples of schools at multiple levels just going to completely like online-based laboratories or dry laboratories. So, given that laboratories are uniquely suited for helping students achieve some specific learning goals, but they're also really expensive to staff and run, we find that current studies are really needed to assess the value of laboratories in terms of encouraging science learning. So, that's where our study of concurrent and non-concurrent enrollment comes in. We find that most scientists and educators would probably agree that laboratory experience is pretty essential for learning chemistry, but even so, a recent survey of course guides that I did over the last year reveals that when we look at 40 public universities from across the nation with high undergraduate enrollment, we find that a substantial number, around a third to up to 43%, are offering these introductory science courses separately without requiring concurrent enrollment. So you can see the breakdown at Michigan in introductory biology, chemistry, and physics. Students are all able to take the course non-concurrently. So this is really an issue across the nation. We've looked at schools. The 40 schools that we surveyed were from conferences varied geographically. So this separation does provide some, we'll call them perceived benefits. So universities might not have the physical space to accommodate all laboratory students in a given term, or all lecture students in a given term in the laboratory. It can, of course, ease the financial burden of the laboratory on the department if you offer non-concurrent enrollment and not everybody has to take the laboratory, and then you don't have to pay for as many students to take it. As one department had aptly stated here at the university, said, well, then if you take, a 5-credit course, if you fail it, you have a bigger risk, but if you have a 2 and a 3-credit course, then you can, fail one but still get credit for the other. So I translated that. Reduces the risk of taking a 4 or 5-credit course. And of course, taking courses non-concurrently can help, or offering separate courses can help to deconvolute students' grades. So if you have a student who performs really well in the lecture, but not so well in the laboratory, you have 2 sets of grades that sort of more accurately reflect that. So there may be some advantages to offering non-concurrent enrollment, but there are also advantages to having a single course or at least requiring concurrent enrollment. So previous literature has shown that encountering the same concept in multiple contexts can promote transfer, and laboratory experiments without sort of other supporting features, discussions, group work, have not been found to really promote interest in science as much as paired work has. And there's other studies that show that concurrent enrollment can heighten the reasoning skills of lower ability students too. So there's been a few previous studies of concurrent and non-concurrent enrollment, but overall very little has been published on the impact of the timing of the laboratory in comparison to the lecture. So over the evolution of this project, which, as Mark said, really started when I got here, we've really only found 2 specific studies that address the question of concurrent and non-concurrent enrollment. You can see they're both pretty dated. Well, they're both dated. I have to be careful. You can see that in the top case, this group looked at general biology students at the community college level. Over a year, they studied 500 students and found that concurrently enrolled students had higher exam scores and more positive attitudes than non-concurrently enrolled students. And similarly, in a physics course, concurrent enrollment helped the final grades of, quote, middle students, so students who came in with, quote, middle-of-the-road GPAs. And that study looked at 2,500 students over 5 years. Now, it's true that the proportions of the demographics of students have changed since the 70s and 80s. So our study is not only current in terms of demographics, but we also probe a much larger data set over more years than either of these studies. And so this leads us to the specific context of our study, which is general chemistry at University of Michigan. So our data set covers more, like I said, more students over more years. And as I said, the proportion of female, Hispanic, Asian, Black students has increased steadily over the past few decades. And so to the best of our knowledge, this data set really has no counterpart in the literature in terms of student body size or number of years studied. And because of the aforementioned benefits of concurrent enrollment that I just talked about, we hypothesized that concurrent enrollment for students in our class would positively impact students' final grades as well as their retention rates. And we also thought that general chemistry at our university would specifically be an interesting context in which to look at this because of the really intensely collaborative nature of the laboratory course. So there's a large body of literature that I'm sure some of you are more familiar with than I am that really supports that collaborative work is beneficial to students in a number of ways. Okay. So general chemistry at the University of Michigan. Of course, there's not just one path. There's never just one. Students have the option of taking the lecture in one of three different formats. The regular, quote, or traditional lecture format meets 3 hours per week. The Comprehensive Studies Program, or CSP lecture, is designed for students who are expected to benefit from extra in-class time and extra GSI office hours and being with an experienced instructor. And that class meets for 4 hours per week. And all of the evaluations across the regular lecture and the CSP lecture are the same. So they have the same exams, they have the same sorts of quizzes and homework and all this. And I should mention that the regular lab course that goes with either of these lectures is not explicitly linked in terms of the material that it teaches in any way. So there's basically no alignment between the two courses. So other than being both general chemistry courses, there's no structured alignment between the two. And like Mark mentioned, the studio course integrates the laboratory and lecture into a single 5-credit course. So obviously you can't have non-concurrently enrolled students if they're just taking a 5-credit course or not. And Mark also mentioned that one of the ideas behind doing the studio course was to evaluate students in really different ways than they were being evaluated in the regular lecture and in the CSP lecture. And so because of those different grading schemes in the studio course versus the rest of the courses, the studio students were not included in the regression analyses that I'm going to describe. So you can see that the bulk of students are enrolled in the regular lecture and the remaining 9% in any given year are roughly evenly split between the other two. Okay, so with the exception of studio, students are not required to concurrently enroll. And if we look at the number of students that concurrently and non-concurrently enroll in our data set, we find that 63% are concurrent and 37% are non-concurrent. Now, roughly half of the non-concurrent students are taking the lecture first and the lab in a later term, and roughly half are taking the lecture and then the lab never, or they never enroll in the lab. Maybe they switch programs or whatever. They don't have to take the lab for whatever reason. There's a very, very small number of students that take the lab and then the lecture later. So here the area of the circles is just weighted based on the number of students that are in each category. And you see that if you break down concurrent versus non-concurrent enrollment, according to the percent of students who are in each category, you see that the majority of students in the study that we're talking about are concurrently enrolled and are taking the regular lecture. So we collected students for data. We collected data for students who enrolled in a lecture during a fall term between 2002 and 2007. The reason we did that is because studio was only offered in the fall when it was offered, and so we wanted to control for different types of students who might take sort of a different track, when a, quote, regular student would take it in the fall. And we collected all this other information about them: gender, ethnicity, their high school GPA, placement exam scores for chemistry and math university placement exams, information about some other chemistry courses, and their final grades and if they withdrew, the withdrawal date from the course. So I should note that students who withdrew before the quote normal drop add deadline are not considered withdrawals in this data. And the reason is that the normal drop add deadline is at the end of the first 3 weeks of class, and there's a whole broad range of reasons why a student might withdraw from a course early on in the term. So the withdrawn students that we're talking about are withdrawing in October, in November, in December, right before the final, after the final, whatever. So we used regression models to evaluate the impact of concurrent enrollment on final grades and withdrawal rates from the lecture. For final grades, we use linear regression, and for withdrawal rates, we use binary logistic regression. And I just thought I would put in a little brief reminder for those of you who may not have had to deal with statistics lately, that for linear regression, you just use that to figure out the impact of a predictor variable on a single outcome variable. So this example is, just an example. It shows a regression based on one predictor variable, and in our regressions, we're using 5 predictor variables. So I can't show you that because it's multidimensional space, and it's confusing, and it's hard for me to wrap my head around it. Okay, and for binary logistic regression, it's similar, but it's used when the outcome variable is dichotomous. So for example, withdrawn or not withdrawn. A student really can't partially withdraw, well, at least not formally speaking. So the predictor variables that we used in our regression models were concurrent or non-concurrent enrollment status, which I've already described to you, something called cluster number, which I will describe to you, high school GPA, comprehensive SAT score, and then an interaction term between the enrollment, the concurrent or non-concurrent enrollment variable, and the cluster number. So I've already told you a bit about the numbers of students that concurrently and non-concurrently enroll, but I'll tell you a bit about the other variables. And I should say, if you guys have questions about the regressions as I'm going through them, you should ask. It's probably easier than holding it till the end. So we used high school GPA and comprehensive SAT scores as covariates because they've been found in previous literature to be good predictors of freshman college achievement in multiple contexts. You might wonder why the SAT histogram looks sort of funny. The reason is that some students who come to Michigan only take the ACT, and so I used a concordance table to convert ACT scores to SAT scores, and the table converts a single ACT score to a single SAT score. So the students who are in those spikes really represent a range of students. Sure. So the question is, did we consider using subfactor scores from the SAT? And I would have liked to do that, but because so many of the students used or only take the ACT, it would really cut. It would cut more than 50% of the data out to look specifically at SAT math or SAT verbal or even any of the subscores of the ACT as well. So another covariate or predictor variable that we used is we call cluster number. We partitioned students into 4 clusters according to their scores on university level chemistry and mathematics placement exam scores. You can see the distributions of the math and chem placement exam scores here, that the math exam is designed to draw out the tail of the distribution, whereas chemistry is a little bit more even. So what k-means cluster analysis does is if you plot these 2 variables against each other, and you could use more than 2 variables, just like for regressions, you could use multiple predictor variables for this. The cluster analysis attempts to identify the centers of natural homogeneous clusters in the data. I hope you can see the colors. So here we've partitioned the students into 4 different clusters based on their exam scores, with students in cluster 0 in the blue having the lowest scores overall, and students in cluster 3 having the highest scores overall. And I should note that we did all the analyses that I'm describing here without including the cluster analysis at all. We used the mathematics and chemistry placement exams as continuous variables in the regressions, and the results are the same. The conclusions are the same. The magnitudes change slightly, but the conclusions are the same. So if we look at a histogram, go ahead.
Did you set 4 clusters? Did you tell it to find 4 clusters?
Yeah. You can, when you're doing a clustering analysis, you can tell the method, I want you to spit out 2 clusters, I want you to spit out 20, I want you to spit out 100. And so what I did is I looked at what happens if I dictate 2 clusters versus 3 versus 4 versus 5 and waited until the results sort of stabilized. And it seemed like 4 still made sense. Okay, so a histogram shows that about 41% of students are in cluster 2. These are students who have high math exam scores and sort of mediocre chemistry exam scores. And I just included this percentage breakdown of the students who are concurrent versus non-concurrent across each cluster to show that the percentage of cluster 0 students who are concurrent and non-concurrent and across all clusters is relatively similar. So this indicates that concurrent and non-concurrent students are like relatively evenly spread out throughout the graph, and they're not all concentrated in cluster 3, say, for example. Like all concurrent students are not in cluster 3. Okay, the last predictor variable that we used is an interaction term between cluster number and enrollment status. That's on the bottom right there. And this variable was included to help parse out if there's any interaction going on between enrollment and cluster number. And I'll explain that more when I show you the results. It'll make more sense. So the results of the models. So the result of the regression model for final grades shows that a coefficient on the enrollment term of 0.19, which means that concurrently enrolled students are predicted to have 0.19 higher final grades. We're on a 4.0 scale as compared to non-concurrent students. So this is a pretty exciting result, considering 0.19. If you think of a lecture grade, a lecture grade going from an A- to an A is a 3.66 to a 4. So we're looking at roughly half a letter grade. Okay, the interaction covariate term. This interaction term reveals a differential impact. Okay, I should back up. So the coefficient is negative 0.04, which reveals a differential impact of concurrent enrollment on final grades that's dependent on cluster number. So this means that the amount that concurrent enrollment, quote, helps each cluster is not the same. So if I show this on a graph, so here's that 0.19 up here. This model predicts that the students who are in cluster 0, those who are scoring the lowest on the math and chem placement exam scores, that those students would be helped the most by concurrent enrollment. Those students who are in cluster 3, those students who have the highest math and highest chemistry placement exam scores, are helped the least by concurrent enrollment. And it kind of makes sense, just intuitively. The strongest students who come in, it's not really going to matter if they take the lab at the same time or later. Joe. Can you say it again?
You've got 4 separate categories here for your clusters. Did you consider putting them into 4 separate interaction terms?
Oh, I did not.
I'm assuming a continuous decrease.
We did not. We have not done that. But that's an interesting idea. I should write that down. Okay. So go ahead. Oh, that's just rounding. It is actually positive. If it weren't, that would be a bit of a problem. But it is positive, but it's because the scale of the SAT is so large, the coefficient is actually very, very small. But it still ends up having a relatively big impact on the grade. So the coefficient is probably like 0.00, 7 something. And when you multiply that by 1,200, you get a big effect in terms of the final grade. I should have mentioned that. Well, I'll get to that. There's more to the story. So this is an important result that shows that the students who scored lowest on the placement exams are predicted to be helped the most by concurrent enrollment. Okay, so this is getting at this gentleman's question. Now, even though we've controlled for differences in high school GPA, SAT, and placement exam scores, might there be other confounding variables that we still haven't measured that are contributing to these results that we see, but we haven't measured? Say, for example, more motivated students are concurrently enrolling, or students who just have better, like, I don't know, logical thinking skills are more concurrently enrolling. So we employed a modeling technique to address the issue of this issue of basically prediction bias. And we found that indeed stronger students do self-select concurrent enrollment more often than weaker students do. But through the prediction bias modeling, we see that it doesn't account for the entire effect. So roughly 0.1 out of 0.19 of the increase in final grade units can be attributed to other factors, or we can't pinpoint what the what contribution or what factors that 0.1 is coming from, which means that concurrent enrollment may not be exclusively responsible for the final grade increases we observe in clusters number 2 and 3. Who were retained in the lecture? Yeah, so all of these final grade analyses only include students who are retained. So the students who were withdrawn are not included. Oh. Okay, so the issue of students taking the course a second time. So we only included the first, we looked at the first time that a student enrolled in the course only. Thanks. Okay. Okay, so we know there's a statistically significant positive effect of concurrent enrollment for students in clusters 0 and 1. We can't know with statistical certainty that concurrent enrollment is the reason that we're seeing these higher grades for concurrently enrolled students in clusters 2 and 3, however. Okay, for withdrawal rates, the regression for withdrawal rates shows that concurrent enrollment systematically decreases withdrawal rates from the lecture. So we'll look at this exponentiation of the B coefficient for concurrent enrollment. Comes out to 2.19, which shows that the odds of concurrent enrollment, the odds of a concurrent student being retained in the lecture are predicted to be 2.2 times higher than for non-concurrent students. So this is a pretty important result as well. Basically, a student who's concurrently enrolled after controlling for these other factors is basically twice as likely to be retained in the lecture as a non-concurrent student. So briefly, I'll mention these results from the studio-style course format that Mark talked about. When we compared studio to non-studio students, we found that enrollment in the studio format had no significant effect on withdrawal rates. We did find a statistically significant effect in terms of final grades, but as Mark mentioned, the procedures for assessing the students in the studio course are pretty different, and they weren't standardized at all across the two courses. So even though we see these grade increases for students who are in the studio course is 0.13 and 0.23, depending on which class of non-studio students you compare to, we find that there isn't really, we can't be statistically, there's like a statistical effect, but we're not sure that that represents a real effect of students being benefited by the studio course, at least according to these measures. Question? So the question is the demographic profile of the studio students the same as in the other courses? You know, the first 2 years that the studio course was offered, it drew mainly from honors students in the LSA Honors College. So I don't know the numbers off the top of my head, but for those 2 years I would say no, but
for later years, no as well. In fact, so like year 4 of the course, we had 20% CSP students in the studio, which is far higher than the percentage
That's true.
in the regular course. And we still had complete retention
That's
and
right.
the grade bump. So
That's right. So in the regular lecture course, there's about 7% of students are in the CSP program, whereas in studio it is higher. And then of course in the CSP lecture section it's much higher. It's around, I think, 50% in that case. Question? So the question is, why are we seeing a differential? Why do we see no effect of withdrawal rate, statistically speaking, but anecdotally we saw a lot greater retention of students in the studio course? I think the reason is I think the reason is due to sample size. So when we're looking at comparing 9,000 students to a few hundred students, and then you parse that down to just the students who were withdrawn, we're really looking at, one or a few students who withdrew from the studio course at all over the whole 6 years of the data set. So I'm not positive, but I would surmise that that's the reason why we're seeing no statistical effect. Okay, question?
Yes, we're looking at all those final. All our data is for the very final grade.
Yeah. Okay. So with that, I'll just leave you with our key findings and some potential implications. So in this data set, we found that the students who scored lowest on the university placement exams received the most benefit from concurrent enrollment in terms of their final grades. And importantly, the retention result, the odds of a concurrent student being retained in the lecture are 2.2 times higher than they are for a non-concurrent student. So the next question you have to ask is, why is this the reason? Or why are we seeing these results? And we think that one of the reasons, and we think that the chief reason that we may be seeing these results is the nature of the laboratory course at Michigan. So the nature of the laboratory course at Michigan is really intensely collaborative, and collaborative work has been shown in many contexts, as I mentioned before, and in many disciplines to promote student learning, to help students develop interpersonal skills, to increase metacognitive processes when they have to explain things to one another. And the laboratory course here is really built around the idea of teams doing laboratory experiments. The students produce team lab reports, they do team discussion presentations, they evaluate each other throughout the course of the semester, and we really think that this could be the mechanism by which we're seeing these results. So this work really has the potential to impact students when they're meeting with their advisors. I've talked with some people over at in the advising office for LS&A, and some people have said, oh yeah, well I would always encourage students to concurrently enroll if possible, but I know other advisors who would not say the same thing, and the representation in the sciences in the advising department is not very strong. We also think that there's potential for this work to impact students who are in other chemistry courses, higher level like organic, and other disciplines like bio and physics. So with that, I have to acknowledge Ed Rothman and Joe Krajcik. Ed Rothman at CSCAR, director of CSCAR, and Joe Krajcik from School of Education. He just moved up to MSU. This work really would not have been possible without either of them. Brad Orr in the physics department has been instrumental in some conversations, as well as my lab, the Banaszak Holl group. I was afforded the time to work on this by the Department of Chemistry and also the GAN Fellowship. And we were also awarded a CRLT Investigating Student Learning Grant, which really helped us be able to disseminate the information at some national conferences over the last year. So with that, I'll thank you for your time, and if you have any other questions for Mark or I, we'd be happy to take those. Yes? I guess I'm supposed to run over with the microphone and tell you so you can hear it on the video.
Is there a way to parse out the effect of the actual learning environment in the Concurrent lab versus just spending more time engaging with the material? In other words, if there are 2 extra hours of lecture,
Some fraction of the studio course, and we had no control over that, so we just threw all that data out and never did anything with it, and have no idea whether it was significant or not. It would still be an interesting experiment to do the right way again someday. It's amazing how things can get contaminated. And when we set the whole experiment up, we were saying to the person setting it up, now this has never been seen by anybody, right? But in the end, we turned out some groups have.
Yeah. Yep.
Did all of your students have similar exposure to chemistry and chemistry lab in high school coming in? I know it's a requirement for admission, but if you had a student who had a lab in high school, didn't have a lab in high school, would that have an impact?
Yeah, that's a great question. That's not something I know that we would, well, I don't know that we would have information about that just in the database that we're pulling this demographic information from.
Per student basis in any way, unfortunately. It's an interesting
Yeah.
question.
Yeah.
So I sort of have a 2-part question because I'm one of the advisors that does not have a science background, and so did not know that I should be strongly encouraging students to.
Oh, this is great. Actually, I'm glad you're here.
Example right here, and this is really informative. But one question I had was sort of, what is the number of seats that are available in chemistry 130 versus chemistry 125, 126? Because I was curious to know if this has affected. So this is sort of the second question. It's affected the way that you, or will affect the way that the chemistry department will allot the number of seats to be more in line.
I hope so.
Or if there will be an increase in sort of marketing, involvement and access, sort of how students are strongly encouraged, or students with X scores or something in the placement should strongly consider concurrently enrolled.
Yeah, that's great.
So we have more students taking 130 than we can fit in the 125. That's when Becky mentioned that some schools do it for this reason, she meant us. This is a really shame. Becky didn't mention the instructor of 125 by name, but I will. Nancy Burns has done an amazing job in developing this course. And she's done, one of the things that was fascinating, I said this didn't start out the way we imagined it. We put a lot of effort into having all of these wonderful interactive things going on in the studio course, but then when we compared it directly against what was going on in 125, we discovered that even though it's uncoupled from the main course explicitly in terms of the content, they're doing such a good job in 125 that in fact a lot of the learning goals that we were hoping were coming out in the studio and did come out in the studio still come out in 125. But we do not have enough seats right now. We're kind of waiting to get this paper published. We're going through the review process right now. Once we have an accepted paper, we plan to go visit the dean.
Yep. Sure.
And then that brings to mind, too, another question of, would you have enough data to be able to look at the impact of instructor influence? If you have a certain instructor that has taught a certain number of courses over the year in both studio format non or consistent instructors across, where you can parse it out and look at instructor as a factor, an influencing factor.
It's a great question, with one exception over the last decade or so. The instructor impact on the grades in 130 is in the lecture section is fairly minimal, and that's been looked at because we want to make sure that we're not having that kind of problem. And we also, in the studio, we had 2 people who taught it, and again, we didn't see an effect.
So we don't actually see, there are occasional exceptions, but in general we don't see an instructor effect.
I wonder if your data, if you could talk about the student level. Do you know if they're first year students or their first semester here? Just because, and this is just anecdotally, I think Chemistry 130 is one of the most commonly first science courses that university students take here, and that the 125 would be probably their first lab experience. And since it's such a pipeline, a gateway course for so many of the other sciences, just kind of curious to know if you have any data about that.
Yeah, so the students who are in the general chemistry course at Michigan are basically 90% freshmen, and probably around, so if a freshman is going to take this general chemistry course in the first year that they're here at Michigan, 75% of them will take it in the fall. So the vast majority are first term freshmen in both the lecture and the lab courses. So, yeah.
So, question about how did you may have mentioned, how did you measure withdrawal rate? Is that only from the lecture class?
Right.
And so did you, going back to that risk of taking a full versus not, did you control for the possibility that withdrawing from a lecture in a concurrent class also has the risk of having to withdraw from the lab versus continuing with the lab and getting rid of the lecture and taking the lecture later, so that that could be an impact more, or that could have some percentage of your variance. You understand?
So,
if I'm taking a class concurrently and I withdraw from the lecture, am I still taking the lab for credit, or should I have to withdraw from both? And what does that do to my schedule? What does that do to my credit hours? And what the impact of that versus sticking it out and taking the class?
So you're talking about the studio students then?
No, I'm talking about the ones where they have a choice to take both. If it's concurrent, is it bound together as one full?
No. So a student who is concurrently enrolled could still choose to withdraw from one of the courses.
And that's what you were mentioning, is they withdrew from either one, or they
just withdrawal from the lecture. So actually, according to the way that we took the way that we requested the data, we didn't collect information for students who only enrolled in the lab ever. Just because we weren't thinking about those questions when we selected our data set. And so we actually can't answer the question. We can't answer the flip question of students who are withdrawing from the lab.
I'm just wondering if there's this psychological and all the other impacts of if I withdraw from the lecture but I'm still taking the lab, as because it's concurrently to my schedule now and have to reschedule the lecture for the next semester. Would that have an impact as opposed to if I know I'm not taking the lab till next semester? If I withdraw now, I can take the lecture and I can take them concurrently later.
I don't know. I don't know.
It's just a confounding variable.
Yeah. So I think about it. Yeah.
She asked if you could repeat the question.
So the question was, I don't know if I could summarize it. The question was about whether withdrawals, like if there's some impact, if a student would choose to withdraw when they're concurrently enrolled versus non-concurrently enrolled for some other reason than maybe just having performed poorly in the course to date. So maybe they're thinking, oh, it's going to mess up my schedule a lot, and next term if I take, just the lab by itself, that'll be easier, or something like that. Oh, okay.
I wonder if you have or have plans to look at how the students performed in subsequent courses. Did they continue on in chemistry, for example, or students who were in the concurrent course as opposed to the non-concurrent course? What was their experience like then in subsequent chemistry courses?
Yeah, so it would be really interesting to look at the numbers of students who continue on, the number of students who continue on and take another set of concurrent versus non-concurrent, and what happens to those withdrawn students. We do have some of that data, but we haven't done a lot of work in that in looking into further courses thus far. but it would be an area for a future project.
All right, I think you get the clear lesson that there is a lot of data present on this campus, and it's easy to imagine many more questions than we can possibly digest right now, and that's part of the point of this lecture series. So let's thank Becky and Mark again. And I hope we'll all see you here in 2 weeks for the next seminar.